And now, resistors in parallel. Let's do 3 again. Battery go into a wire, and there's one resistor, R1, but then here, in parallel, is R2, and then here, in parallel, is R3. This is what we mean by parallel, is the wire branches, the current splits, and goes off to different parts of the circuit. So this is 3 resistors in parallel. One thing that'll help you solve these is to realize that the topology, I think is the right word, the topology of the wires doesn't matter. So if we have this circuit, sometimes it helps to realize you can draw it different ways. What really matters about a wire is its potential. That's what determines how much current flows, potential differences. So if we think about the potential, it's the same here, here, it's plus EMF, here, 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 and it's actually the same across, on either side of that branch. Because potential doesn't have to be conserved, it doesn't split up like current does. So it's the positive EMF here, positive EMF here, positive EMF here, all the way to here, because this is all one big piece of continuous perfect conductor. Positive EMF here, positive EMF here. So what I'm trying to get you thinking about is that looks like 2 junctions, and if you were to hook it up this way, it would be 2 junctions, but really, in terms of potential, that's really just 1 junction. It's all 3 of these is a place where the current splits from the same potential. So you could draw the circuit a different way that would be actually exactly the same. So let's do this. This circuit is equal to this circuit. Draw it kind of nice for you like that, where this is R1, R2, and R3. So that's actually a slightly nicer way to draw it, because then you just have 1 junction to think about. Okay. And then it helps to realize that it doesn't really matter how the wires are spaced. Let me draw this for you 2 more ways, just because this is, I like to do this. What if I said, okay, we have 2 in this nice uniform parallel branch like this. And you say, oh, but where's the 3rd? I can say, oh, well, I'll just put it right here. 1, 2, 3, like that. So I made this 3rd one look like a little sort of add-on to number 2, and I shifted 2 over. None of that matters in the circuit. That's just manipulating wires. As long as you don't have to cut a wire to reshape a circuit, you're not going to affect it. I can even draw it one more way. Let me draw it one more way, and then we'll actually solve it. Oh, look at this. A triangle. A perfect triangle. It doesn't even matter if it's equilateral or isosceles. R1, R2, R3. It's the same thing. There, that junction is the same as that junction. Here it's a single junction coming together. Here they kind of come together separately, but ultimately it's the same current flows. Doesn't matter. So usually, sometimes when you're new at this, you might realize drawing it a certain way makes it easier to apply Kirchhoff's rules. And the way that wins here is this way, because there's only 1 junction to think about. You don't have to worry about the fact that, wait a minute, there's multiple junctions, it's confusing. So let's solve it from that middle diagram. Yes, there. Very nice. A reminder, this is the EMF with a battery here, and this is, I got a little sloppy here. This is R1, R2, and R3. All right. And they're in parallel. Let's see, what are we going to do? So remember, we're looking for find the equivalent resistance. Because again, the battery doesn't know if they're in series or parallel. It just senses some amount of resistance, so it throws out a current. So we're trying to get it in this form. E equals I REQ. But this time, since it's parallel and there's junctions, the current won't be the same everywhere. So we have to actually think about the current coming out of the battery. I'm going to put a T on it for total. So the battery sends out I. I'm going to put a capital T, because that just looks like a plus. the battery sends out a total current using its EMF, and it's sensing some equivalent resistance. But we know that current is going to split up here into the 3 branches. So we actually have to come up with a current for each branch. I1, I2, and I3. Each of those is going to have its own current, and then they're going to come back together for that junction right there. And if I total splits up and recombines, it's still going to be I total, because it has to be conserved. So you'd want to think your way through that before you start doing the equations. So next, you would apply the junction rule. All right, so either junction doesn't matter. If you try to apply it twice, you're going to find that you're just solving for the same thing. You're going to get the same result from both of those junctions. So we would say the sum of, what was the junction rule? The sum of the currents into the junction equals the sum of the currents out of the junction. So going into this junction is I total, and coming out of the junction is I1 plus I2 plus I3. So that's simply saying the conservation of the charge and the conservation of current, however much I1 flows in here, equal to the sum of the current in each branch. Okay. And next, we would apply the loop rule. Oh, right, yes. Oh, I forgot we have to apply it 3 times. I should have left more room. Apply the loop rule thrice. Okay, so the key is to know what loop to apply it to. So some of this kind of analysis is a little bit of experience. You'll get good at it. We're just going to do the easiest, the simplest circuits. Let's see, how do you apply the loop rule again? First, you got to define the currents and which way they're going. So we did that. We said IT comes this way. I didn't draw the arrows, but I1, I2, and I3, we're going to see are going down. And they come back together to make I total. Okay. And then you got to figure out what direction you're going to loop. And I always just draw this and say I always loop clockwise, because that's the kind of guy I am. But then one difference here is if you're doing this loop, you got to stay with one of the wires, and at a branch, you have to decide which branch are you taking in this loop. Right? So if I was going to learn things about resistance 1 and current 1, I would probably loop like that. That's 1. If I were going to loop and learn about resistance 2 and current 2, I would loop like that. And if I want to learn about R3, I would loop like this. And every loop gives you another equation. So let's do them real quick. Let's see. The first loop through 1, would be we go positive EMF is the voltage, the potential difference here, and then minus I1 R1, because we're looping with the current, so the potential drops. Minus I1 R1 equals 0. All right, and then if we loop the second loop, I'll just write them in turn. The same EMF minus I2 R2 minus I2 R2 equals 0. And then the third loop, the EMF minus I3 R3 equals 0. So physically, what that actually is telling us, you can actually tell just by looking at it, you're applying an EMF to each one of these. It's almost like they're individual little circuits. Right? Positive EMF here, 0 volts here, you're applying EMF to R1, and you're going to flow I1. So since I'm running out of board, if you'll allow me, I'm going to move this over, call that equals, and erase that. All you're really saying is we're applying V equals IR to each one of these, because I know what the delta V is. It's the EMF. Let's see, so now all we got to do is combine these, and you're trying to get to something like this, so it might be a little hard to see it, but the best is to take these 3 things and stick them into here. That's what you want to do, and we're going to use that. Because we're going to say, here is the current total, that's the EMF over REQ. I1 will go here, EMF over R1. I can hear some of you getting excited. I2 is the EMF over R2. And I3 is the EMF over R3. Did I say I2? I meant to say R2. Cool, and then now if you cancel those EMFs and you divide that out, you get the famous expression for resistors in parallel. 1 over the equivalent resistance is 1 over R1 plus 1 over R2 plus 1 over R3, and we could keep going if we wanted to have more. So there you go, parallel resistors. If you just want to memorize it, you can, but I'm just showing you where it comes from based on Kirchhoff's rules.